Here we're going to look at exponential functions. We're going to talk about graphing them and determining whether they are growth or decay, determining their y-intercept and asymptote and domain and range. So to do this, I'm going to be creating a table in Desmos. So I'm going to walk you through how to do that. So this first equation I'm going to type in, we've got y equals 4 parenthesis 2 to the power of x. An exponential equation is when you have your variable, the x value, in the exponent. So right now, let me adjust the window here. It's kind of gotten to some weird settings. I'm going to make it just be like -10 to 10. And -10 to 10. So you can always edit your window if it's kind of in a weird place by going into here and adjusting that. The step is what it counts by. So here we've got a normal window. We can see the graph. You can see that it's sort of like a J shape, and you can see that it's going up. This is how I know whether it's growth or decay, is whether it's going up as you go to the right or if it's going down as you go to the right. You can also tell by the value in the parentheses. If that value, which is known as a base, the base to the exponent, if that number is greater than 1, it's going to be growth. And if this number is less than 1, like 1/2, 1/3, something like that, it will be decay. If you want to take this equation, you want to make a table out of it. You click in where you're entering it, you click this gear, looks like a flower, and then you click this one that looks like a table. And that's going to give you a table of values. Our typical values are -2 to 2, but if you'd like to add any more values, you just click down here and you just type in the number that you'd like to see. So I'm going to use those values to graph over here on my paper. So I've got -2 is at 1, -1 is at 2, 0 is at 4, 1 is at 8, and 2 is at 16. And as you can see over here, it's just flattening right here, this flat part of it. You're going to notice that it's getting very flat and it's never going to actually touch the x-axis. It just gets very, very close to it. And I'm terrible at drawing on the computer like this. Ooh, I missed that. Anyhow, put the dots on there. We'll go by your dots rather than your graph, but this is growth. The y-intercept, where it's crossing the y-axis, is the 0.04. The asymptote is going to be, it is a horizontal line, so you're going to say y equals, and it's always going to be where it's getting flat. Here it's getting flat at 0. And honestly, you'll be able to tell because when you look at your equation, if you have a plus or a minus afterwards, like these down here on the bottom, has a -1 and a +3, those values are where your asymptote is going to come from. So if it doesn't have a plus or a minus after it, the asymptote will be y equals 0. The domain is all real numbers. I'm going to use the super R for that. And the range is going to be y greater than whatever your asymptote value is. So y greater than 0. Not equal to it, just greater than. So we're going to look at the next one. So I'm going to go over here, get rid of that. I'm going to type in my new equation. Y equals 8, and then 1/2. And then, oops, the exponent, pushing a to the b to get that exponent of x. You can see that it's going downward as it goes to the right. So it is a decay because it's decreasing. And I'm going to make a table out of it so I can see some values for plotting. So -2 is at 32, which is off my grid. -1 is at 16. 0 is at 8. 1 is at 4. 2 is at 2. If we wanted to add some more here, if I add 3, 3 is at 1. If I added a fourth one, 0.5, you can see that it's just going to get really flat. If I look over here, if I pull the graph a little bit to the right, you can see it flattens out above the x-axis. Terrible graphing of lines here. Anyhow, decay is what it is. This is decreasing. The y-intercept is the 0.08. The asymptote, y equals 0. The domain, all real numbers, and the range, y greater than 0. These don't have any x-intercepts, so if it does ask you about x-intercepts, you would say none. Do not put the number 0, put the word none. All right, when they add an asymptote like this, -1 and this +3, the -1 is going to move it where the asymptote is down 1, which means we could have an x-intercept. So if they do ask you for that, know that you can have that. It could happen. We're going to go over here. We're going to edit our equation. So we've got y equals 4, parenthesis 3 to the power of x, and then -1. You can see that this is growth. You can see that it does go underneath the x-axis there, and that's because this -1 brings that the J shape down 1. It's a vertical shift of down 1, like the transformations that we studied before. So it's a growth because it is going up. I can make it into a table so I can plot some points from it. -2 is at -0.55. -1 is at 0.33. 0 is at 3. 1 is at 11. 2 is at 35 way off the page. And then it's flattening out down here. So the y-intercept is at 0.3. The asymptote is y equals -1. If this is a -1, your asymptote's y equals -1. If this was a +1, it's y equals +1. If it was a -5, this would be a -5. It's always coming from that number. The domain, all real numbers, and the range, it's above that -1 value, so it's going to be y greater than -1. And for the last one here, just typing in the equation, y equals 2, parenthesis 1/2. Whoa, or maybe I'm not typing anything. Y equals 2, parenthesis 1/2, then exponent of x, and then +3. There we go. You can see that the J shape is elevated up at the value of 3 there. And let's make a table out of it. So plot some nice points on our graph. -2 is at 11. -1 is at 7. 0 is at 5. 1 is at 4. And 2 is at 3.5. You can see that right here, this would be the value of 3 where it's flattening out. It's never going to actually touch 3, but it gets infinitely close to it. So this is a decay because it goes down as it goes to the right. The y-intercept is the 0.05. The asymptote, y equals 3. The domain, all real numbers. The range, y greater than 3, as I write 0. Y greater than 3, because everything is above 3 for the y values. And that's how you graph exponential growth and decay.